Hello students, welcome to EPG Pathshala. I am Dr. Anjali Sharma from University of Delhi. Today we are going to talk on module 4 probe and 2 probe methods Pauw method under the paper Characterization of Materials Part 1. So after completing this module, students will be able to understand measurement of resistivity, 4 probe method, 4-point measurements on a thin film, 4-point method for thick film resistivity measurement, and Pauw method. The potential probe is most commonly employed method for measuring the resistivity of samples with low resistance value. Potential drop across two probes is measured and the gap between them d is taken as the sample length L. If the probes are not point contacts, true value of probe distance is gap between the centers and not the shortest distance between them. So figure on the screen displays the schematic demonstration of the experimental procedure. Resistivity rho becomes equals to Vd into A divided by D into I. Probe method equally applies to single crystal or bulk samples and can determine their resistances. Current flows through outer contacts near the sample edges and potential difference is gauged across inner contacts. Hence, effect of interfacial resistance between electrodes and sample is eliminated. Thus, it is precise technique for low resistance measurements. Though the contact and the probe resistance themselves are cancelled out, there is still possibility of error in measurements if the contacts procedure heat. Therefore, low resistance of contacts is preferable. The error due to DC offset in the instrument is readily overcome by subtraction. Additional self-induced voltage offsets within circuit can increase the error. This may be rectified by flowing reverse current in the sample. A sample voltage of order of few microvolts might develop across the sample, thereby adding signal noise and increases the error. This error can reduce by shielding the cables, single point grounding, etc. The following conditions are required to satisfy the resistivity measurements of a semiconductor. The material possesses uniform resistivity in the measurement area. Second, if minority carriers are injected in semiconductor via the current conducting electrodes, much of these carriers recombine at the electrode and they have negligible influence on conductivity. Third, surface to place the probe should be flat without any surface leakage. Fourth, the probes employed in measurement should touch the surface in straight line. Fifth, diameters of contacts between the probes and the semiconductor should be smaller than the gap between the probe. And lastly, the material surface can be either conducting or non-conducting. The boundary is conducting when a material having lower resistivity is deposited. Non-conducting boundary results from plating the semiconductor surface insulator. Now students, let us see its applications. Remote sensing area, resistance thermometer, induction hardening processes, precise estimation of geometrical factors, characterization of fuel cells by polar plates. A simple ohmmeter can be used to measure the resistance of the contacts, samples and cables connected to the samples. In case of electrical contacts created with micromanipulators, the measurements of contact resistance become challenging due to small contact area. The problem of the contact resistance can be overcome using a 4-probe configuration. In this method, the current flows through the outer two probes while the voltage is measured across the inner probe as shown on the screen. The current is injected in the sample through contact 1 and leaves the sample at contact 2. Rs represents the resistance of the sample and Rm represents the equivalent resistance of the voltmeter. Vs represents the voltage across the sample and Vm is the measured voltage.
Now students, let us see about 4-point measurements on a thin film. As the current I is injected through the point contacts placed on the sample, which is a thin conducting film having a uniform resistivity ρ, the current spreads radially and the current density around the contact is given by J is equals to I divided by 2 pi Tr into R unit vector. If two current contacts are placed on a thin film of thickness T and current I12 is injected at position R1 into the surface while extracted from position R2, then the currents are being added producing following dipole pattern as shown on the screen. The thin film approximation is valid only if there is interspacing between the contacts is much larger than the film thickness. In such case, the current density can be expressed as vector J equals to I12 divided by 2 pi T into R vector minus R1 vector divided by mod of R vector minus R1 vector whole square minus R vector minus R2 vector divided by mod of R vector minus R2 vector whole square. Electric field can be obtained as the product of resistivity ρ and current density as E vector equals to ρ into J vector equals to ρ into I12 divided by 2 pi T into R vector minus R1 vector divided by mod of R vector minus R1 vector square minus R vector minus R2 vector divided by mod of R vector minus R2 vector whole square. The measured voltage across R3 and R4 can be obtained by integrating the electric field from R3 to R4. Thus, the potential measured as R4 with respect to the potential at R3 can be expressed as V43 equals to minus rho I divided by 2 pi T into integral from R3 to R4 of R vector minus R1 vector divided by R vector minus R1 vector square minus R vector minus R2 vector divided by R vector minus R2 vector square into d R vector. Since measured voltage does not depend upon the path taken for its measurement, so we will integrate first in x direction and then in y direction. So V43 is equals to minus rho I12 divided by 2 pi T into integral from x3 to x4 of x minus x1 divided by x minus x1 square plus y3 minus y1 square minus x minus x2 divided by x1 minus x2 square plus y3 minus y2 square whole into dx minus rho I 1 2 divided by 2 pi t into integral from y3 to y4 of y minus y1 divided by x4 minus x1 square plus y minus y1 square minus y minus y2 divided by x4 minus x2 square plus y minus y2 square into dy. The voltage obtained after performing integration can be expressed as V43 equals to rho into I12 divided by 4 pi t into L31 minus L32 minus L41 plus L42. Here Lmn equals to ln of xm minus xn square plus ym minus yn square. Thus, the resistivity can be obtained as rho equals to 4 pi t into V43 divided by I12 into L31 minus L32 minus L41 plus L42 whole raised to power minus 1. When the thickness of conducting film is not known, the term R square, that is the sheet resistance, is provided. Sheet resistance denotes the resistance of a square of the film. So R square is equals to rho L divided by Wt equals to rho by T equals to 4 pi V43 divided by I12 into 1 divided by L31 minus L32 minus L41 plus L42. Now next is 4-point methods for thick film resistivity. A current I is injected through the contact placed on a flat surface of the sample. The sample is assumed to possess a uniform resistivity of rho. This current spreads radially and current density underneath the contact can be expressed as J vector equals to I divided by 2 pi r square into r unit vector. The current density due to the current I12 injected into the sample from R1 and collected at R2 by placing two current contacts on flat surface can be expressed as J vector equals to I12 divided by 2 pi into R vector minus R1 vector divided by mod of R vector minus R1 vector cube minus r vector minus r2 vector divided by mod of r vector minus r2 vector cube. Consequently, thick film approximation requires the distance between the contact to be much shorter than the film thickness. The product of resistivity and current densities gives the electric field as E vector equals to rho into J vector equals to rho into I12 divided by 2 pi into R vector minus R1 vector divided by mod of R vector minus R1 vector cube minus R vector minus R2 vector divided by mod of R vector minus R2 vector cube. The potential at R4 with respect to R3 is V43 equals to minus rho I divided by 2 pi into integral from R3 to R4 into R vector minus R1 vector divided by mod of R vector minus R1 vector cube minus R vector minus R2 vector divided by mod of R vector minus R2 vector cube into dr. In the xy plane, the voltage can be found by integrating first in the x and then in the y direction as V43 equals to minus rho I12 divided by 2 pi into integral from x3 to x4 into x minus x1 divided by x minus x1 square plus y3 minus y1 square whole raised to power 3 by 2 minus x minus x2 divided by x minus x2 square plus y3 minus y2 square whole raised to power 3 by 2 dx minus rho I12 divided by 2 pi into integral from y3 to y4 y minus y1 divided by x4 minus x1 square plus y minus y1 square whole raised to power 3 by 2 minus y minus y2 divided by x4 minus x2 square plus y minus y2 square whole raised to power 3 by 2 into dy. The voltage obtained after performing integration can be expressed as V43 equals to rho I12 divided by 2 pi into 1 divided by S41 plus 1 divided by S32 minus 1 divided by S31 minus 1 divided by S42, where Smn equals to under root of xm minus xn square plus ym minus yn square. So finally, the expression for the resistivity of a thick film is rho equals to 2 pi V43 divided by I12 into 1 divided by S41 plus 1 divided by S32 minus 1 divided by S31 minus 1 divided by S42 whole raised to power minus 1. Current density below the contact is given by J vector equals to I divided by 2 pi r square into r vector. The current density due to the current I12 is given by J vector equals to I12 divided by 2 pi into r vector minus r1 vector divided by r vector minus r1 vector mod cube minus r vector minus r2 vector divided by mod of r vector minus r2 vector cube. If the contacts are near the edge of the sample, boundary effect appears which need to be considered. This can be achieved by placing two image current sources near the edge of the sample. These additional current sources are mirror images of the real current sources, and the arrangement is shown on the screen. The expression for current density changes to accommodate the additional current sources as J vector equals to I12 divided by 2 pi into r vector minus r1 vector divided by mod of r vector minus r1 vector cube minus r vector minus r2 vector divided by mod of r vector minus r2 vector cube plus r vector minus r3 vector divided by r vector minus r3 vector cube minus r vector minus r4 vector divided by r vector minus r4 vector cube. The electric field becomes E vector equals to rho J vector equals to rho I12 divided by 2 pi into r vector minus r1 vector divided by mod of r vector minus r1 vector cube minus r vector minus r2 vector divided by r mod of r vector minus r2 vector cube plus r vector minus r3 vector divided by mod of r vector minus r3 vector cube minus r vector minus r4 vector divided by mod of r vector minus r4 vector cube. Similarly, the voltage between positions r5 and r6 on the surface can be obtained by integrating the electric field from R5 to R6. Thus, the potential at R6 with respect to the potential at R5 is V65 equals to minus rho I12 divided by 2 pi into integral from R5 to R6 R vector minus R1 vector divided by mod of R vector minus R1 vector cube minus R vector minus R2 vector divided by mod of R vector minus R2 vector cube plus R vector minus R3 vector divided by R vector minus R3 vector cube minus R vector minus R4 vector divided by mod of R vector minus R4 vector cube into dr vector. In the xy plane, thus the voltage can be calculated as V65 equals to minus rho I12 divided by 2 pi into integral from x5 to x6 of x minus x1 divided by x minus x1 square plus y5 minus y1 square whole raised to power 3 by 2 minus x minus x2 divided by x minus x2 square plus y5 minus y2 square whole raised to power 3 by 2 plus x minus x3 divided by x minus x3 square plus y5 minus y3 square whole raised to power 3 by 2 minus x minus x4 divided by x minus x4 square plus y5 minus y4 square whole raised to power 3 by 2 into dx minus rho I12 divided by 2 pi into integral from y5 to y6 of y minus y1 divided by x6 minus x1 square plus y minus y1 square whole raised to power 3 by 2 minus y minus y2 divided by x6 minus x2 square plus y minus y2 square whole raised to power 3 by 2 plus y minus y3 divided by x6 minus x3 square plus y minus y3 square whole raised to power 3 by 2 minus y minus y4 divided by x6 minus x4 square plus y minus y4 square whole raised to power 3 by 2 dy. The resulting voltage from the above integral comes out to be V65 equals to rho I12 divided by 2 pi into 1 divided by S61 plus 1 divided by S63 plus 1 divided by S52 plus 1 divided by S54 minus 1 divided by S51 minus 1 divided by S53 minus 1 divided by S62 minus 1 divided by S64 where Smn equals to under root of xm minus xn whole square plus ym minus yn whole square. Finally, the expression for resistivity is rho equals to minus 2 pi V65 divided by I12 into 1 divided by S61 plus 1 divided by S63 plus 1 divided by S52 plus 1 divided by S54 minus 1 divided by S51 minus 1 divided by S53 minus 1 divided by S62 minus 1 divided by S64 whole raised to power minus 1. Two-probe method. The two-probe method technique is suitable for measuring resistivity of high resistivity samples, for example polymer sheets and films, etc. So as shown on the screen, the resistivity is calculated from the voltage drop V and current I as rho equals to VA by IL.
Advantage of four-probe method over two-probe method. Four-probe method is preferred than two-point probe as the contact and spreading resistance in two-point probe are large and the true resistivity cannot be actually separated from measured resistivity. In the four-probe method, contact and spreading resistance are very low with voltage probes and hence accuracy in measurement is usually very high. To measure very low resistance values, four-probe method is used. The resistance of probe will not be added to that of sample being tested. It is used two wires to inject current in the resistance and another two wires to measure the drop against the resistance. Van der Pauw method. The Van der Pauw technique is employed to determine resistivity and Hall coefficient of a material. It can accurately measure the sample's property having any shape if sample is two-dimensional, solid, without holes and electrodes positioned on its perimeter. It uses 4-point probe positioned around the perimeter of the sample rather in a straight line. Therefore, this method measures the average resistivity of the sample, while the linear arrangement measures resistivity only in the measuring direction. This difference is crucial to anisotropic materials, which can be efficiently characterized by Montgomery method, an extension of Van der Pauw method. Following properties of a material can be measured by this method, like resistivity, doping type, whether it's a p-type or n-type, sheet density of majority carriers, that is majority carriers per unit area, charge density and doping level, mobility of the majority carriers.
Conditions. The following condition must be met in order to apply this method. So first is sample must be flat shaped and uniformly thick. Sample should not possess isolated holes. Sample should be isotropic and homogeneous. Contact should be placed at the sample edge. And lastly, contact area of individual contact must be smaller than the sample area, at least by an order of the magnitude. So next let us see about the Van der Pauw method to determine the resistivity of the uniform sample. This technique was invented by Van der Pauw and is extensively employed in semiconductor industry for determination of resistivity of uniform samples. The technique requires an arbitrarily shaped thin plate sample having four very small ohmic contacts placed on the periphery, usually at the corners of the plate. So as shown on the screen, the schematic arrangement of a typical Van der Pauw experiment. In order to determine the resistivity of a uniform sample, the sheet resistance Rs needs to be determined. As demonstrated by Van der Pauw, two characteristic resistances Ra and Rb are associated with the corresponding terminals as shown on the screen. These characteristic resistances Ra and Rb are related to the sheet resistance Rs through the Van der Pauw equation as exponential of minus pi Ra divided by Rs plus exponential of minus pi Rb by Rs equals to 1. The above equation can be solved to obtain Rs. Thus, the bulk resistivity is obtained from Rs as rho is equals to Rs into D. For determining Ra and Rb, a DC current I is applied across contact 1 and 2 and the voltage V43 is measured across contact 4 and 3. Similarly, the voltage 1 and 4 is measured across contact 1 and 4 by applying current across contacts 2 and 3. So, Ra and Rb can be obtained as Ra equals to V43 divided by I12 and Rb equals to V14 divided by I23.
So students, let us now summarize what we have learnt in this module. We have seen the difference between 2-probe and 4-probe methods of resistivity measurements. We also seen how 4-probe method is used to determine the resistivity of thin film. What are the advantages of 4-probe method over 2-probe method? Which property of material can be measured by Van der Pauw method? Thank you.